Hi, my name is Keshav of CSC Data Science. Today we are going to discuss about linear algebra and calculus. In linear algebra and calculus, we are going to discuss about Gauss-Jordan method. Linear equations by Gaussian elimination, which we transform the augmented matrix to row echelon form. It is also possible to solve the equations by further reducing the augmented matrix to reduced row echelon form, a procedure known as Gauss-Jordan elimination. We pointed out there that if a matrix of coefficients is a square, then provided its determinant is non-zero, its reduced echelon form is the identity matrix. How to determine a matrix inverse? Of course, there is only possible of a square matrix with non-zero determinant using Gauss-Jordan elimination. It is also possible to solve equations by further reducing the augmented matrix to row echelon form by reducing it. A procedure is known as Gauss-Jordan elimination. The transpose of the matrix of cofactors divided by determinant with Gauss-Jordan reduction, the number of operations to invert an n into n matrix of order n cube. There are n square for them, so the operation count is order n power 5, which is much bigger than n cube for large n. Even worse is to evaluate the cofactors by expanding along a row or column, repeating for successively smaller cofactors until one gets down to 2 into 2 square matrix, which are evaluated explicitly. We pointed out there that if the matrix of coefficient is square, then provided its determinant is non-zero, its reduced to echelon form is the identity matrix. The number of operations grows like n factorial, which increases so fast that it would take the age of the universe to find determinant of 25 into 25 matrix. The transformations used in a row reduction are interchange of two rows, multiply a row by a constant, add a multiple of one row to another. Each of these operations can be regarded as multiplying the matrix on the left by another matrix which does the transformation. Even worse is to evaluate the cofactors by expanding along row or column, repeating for successively smaller cofactors until one gets down into 2 into 2 matrices which are evaluated explicitly. As an example, we suppose we have 3 into 3 matrix and we want to add k times row 2 to row 1. This is accomplished by multiplying on the left by, and here is the matrix of 1 k 0 0 1 0 0 0 1. Since we multiply by a11 a12 a13 a21 a22 a23 a31 a32 a33, then we get the matrix of a11 plus k21 a12 plus ka22 a13 plus ka23 a21 a22 a23 a31 a32 a33. We perform a sequence of row transformations to transform the matrix A to the identity matrix and simultaneously perform the same sequence of operations on the identity matrix 1. Each of these operations can be regarded as multiplying the matrix on the left by another matrix which does the transformation. Suppose these transformations are carried out by multiplying by the matrix x1 first, then x2, x3, etc., and finally xp. Then xp into xp minus 1 and so on up to x2, x1a is equal to I. Note the order of operations. Hence, xp, xp minus 1 and so on up to x2, x1 is equal to A inverse, since A inverse A is equal to I. Applying the same transformations to identity matrix, we get xp, xp minus 1 and so on up to x2, x1 is equal to A inverse 1 minus A inverse, i.e. inverse of matrix A. In other words, if xp into xp minus 1 and so on up to x2, x1 A equal to I, then xp into xp minus 1 and so on up to x2, x1 I is equal to A inverse. And here the equation is given below. We will perform a sequence row of transformations to transform matrix A to identity matrix and simultaneously perform the same sequence of operations on the identity matrix. And now we are gonna explain the example 1 of Gauss-Jordan method. The given matrix A is equal to 1 minus 1 0 0 1 1 2 2 0. Start by writing A and the identity matrix side by side and then performing row operations in each case where we add multiple of one row to another. The pivot element is shown by putting a box around it and coloring it green. And here the given matrix applied Gauss-Jordan method. Here the green colored ones are pivot element and 1 minus 1 0 0 1 1 2 2 0 is multiplied by identity matrix 1 0 0 0 1 0 0 0 1, and we are doing the transformation of row 3 to row 3 minus 2 row 1 2 into row 1. Then we are going to get final answer of 1 minus 1 0 0 1 1 0 4 0 into 1 0 0 0 1 0 minus 2 0 1. And then again take the middle element of A 2 3 1 minus 1 0 0 1 1 0 4 0 and identity matrix the we got above 1 0 0 0 1 0 minus 2 0 1, doing row 3 to row 3 minus 4 row 2 1 minus 1 0 0 1 1 0 0 minus 4 1 0 0 0 1 0 minus 2 minus 4 1. And the solution continues as like this. By doing the row transformations and elementary row transformation, we get the final answer of the right side of equation 5. The left hand matrix, which started as A, has been transformed into identity matrix, so that right hand matrix, which started as an identity matrix, has been transformed into A minus 1 or A inverse. Thus A inverse is equal to 1 by 2 0 1 by 4 minus 1 by 2 0 1 by 4 1 by 2 1 minus 1 by 4. It is easy to verify by multiplying out the terms that minus 1 1 0 0 1 1 2 2 0 into 1 by 2 0 1 by 4 minus 1 by 2 0 1 by 4 1 by 2 1 minus 1 by 4 is equal to, and we get the identity matrix as 1 0 0 0 1 0 0 0 1 as required. While this evaluation of the matrix inverse might seem rather laborious, we note that much of the work is copying unchanged rows from line to line, which is trivial and does not have done at all by computer code in computer evaluation. The crucial point is the operation count only increases slowly with n, like n cube rather than n factorial. If one causes uses Cramer's rule and evaluates the determinants the textbook way, expanding along row or column. Even worse is to calculate the cofactors by expanding along row or columns, repeating for successively smaller cofactors until one gets down into n into n matrices which are evaluated explicitly. The number of operations grows like n factorial, which increases so fast that it could take age of the universe to find determinant of 25 into 25 matrix. Each of these operations can be regarded as multiplying the matrix on left by another matrix which does the transformation. The transpose of the matrix of cofactor divided by determinant with Gauss-Jordan reduction, the number of operations to invert an 2 into 2 matrix of order n square. Thank you.